Hello, my name is Ravi Kumar. I am a PhD scholar at Department of Physics, IISc Bangalore. This is a short introduction video to my poster presentation at qmat conference 2021. When a two-dimensional electron gas is subjected to a high magnetic field, then kinetic energy of the electron is quantized and we get discrete gapped energy levels called Landau levels. Due to confining potential, all the low energy transport occurs at the edge of the sample. The conductance in quantum Hall system is given by G is equal to nu E square or H, where nu is the filling factor, meaning how many Landau levels are filled below the Fermi energy. If nu is integer, we call it integer quantum Hall system. Soon after the discovery of integer quantum Hall, fractional value of nu were observed, which were categorized into two divisions. One is electron-like, where nu is less than half, such as 1/3, 2/5, and 3/7, and other is whole-like, where nu is less than 1 but greater than half, such as 2/3, 3/5, and 4/7. For nu is equal to integer and electron-like states, charged current flows in the direction dictated by the magnetic field, and we call it downstream modes. Whereas whole-like state such as nu is equal to 2/3 has a different charge transport at the edge. It was proposed by MacDonald that 2/3 has a non-monotonic density profile at the edge. This gives rise to counter-propagating modes at the edge. Downstream mode with conductance of 1 E square H and upstream mode with conductance of 1/3 E square H. Now, if there is no equilibration between these two modes, the two-terminal conductance for 2/3 should be 4/3 E square H. But if they equilibrate, one gets a monotonic density profile at the edge and an extra upstream mode which does not carry any charge. So we have a downstream mode of conductance 2/3 E square H and a neutral upstream mode. Now this neutral mode is mysterious. One can claim that we have only downstream mode of conductance 2/3 E square H and no neutral mode. So electrical conductance is blind to exact edge structure of the quantum Hall state. To answer this, we have two methods to figure out. One is thermal conductance and another is noise measurement at the edge. Just a short introduction to thermal conductance. As we are talking about quantum Hall, charge flows at the edge. We have two reservoirs, T hot and T cold. The heat current which flows from T hot to T cold is proportional to Th minus Tc, and the proportionality constant is called thermal conductance, which is given by kappa naught T, and this kappa naught T is universal and has a quantized value. Interestingly, kappa naught is same for fermions, bosons, and anyons except the Majorana particles. Now, for Hall-like fractional quantum Hall states, thermal conductance is given by Nd minus Nu times kappa naught T, where Nd is the number of downstream modes and Nu is number of upstream modes. If counterpropagating modes thermally equilibrate, then the thermal conductance is given by Nd minus Nu times kappa naught T, and if they do not equilibrate, then thermal conductance is given by Nd plus Nu times kappa naught T. So we see that even if we have neutral upstream mode, thermal conductance will capture it. In a recent measurement in graphene, thermal conductance for nu is equal to 2/3 state has been found to be 2 kappa naught T in agreement with this regime. But a different edge structure for nu is equal to 2/3, which is co-propagating two 1/3 edge channels, can also give rise to 2 kappa naught T conductance. So there remains a little ambiguity. Now to answer this, we can directly probe the upstream mode in the upstream direction via noise measurements, the details of which I will discuss in my poster presentation. In our measurement, we have observed upstream mode at nu is equal to 2/3 state of graphene and found that these modes are ballistic in nature. Thank you.